heat exchangers for the EMILAB to our institution. Team 11, are you guys ready to start?
Yes, sir. Ready.
Go ahead.
All right, good afternoon, ladies and gentlemen. We are Group 11, and today we're going to be presenting to you our Senior Design Group project, the cooling tower. So before we get started, we're going to go ahead and introduce our dynamic team that helped get this system up and running.
Good afternoon, everyone. My name is Alfredo Araujo.
My name is Dave Garcia.
My name is Gilberto Ponce.
And I'm Marcus Robinson.
And I'm Santiago Orozco.
The goal of our team was to design, fabricate, and test a cooling tower that could be used as an educational tool for a better understanding of thermal fluids, heat transfer, and materials.
So when we learn something, we usually associate with an idea or something that relates to us. So to give you an idea of what a cooling tower is, I'm going to associate Homer Simpson basically taking a selfie at his job. So if you look in the back, those two towers are basically your cooling towers. So in the real world, they look something like this. So on the left side, you have your cooling towers that are associated at a big plant. And then on the right side, it's basically a cooling tower also, in which you would see like in commercial buildings. All right, so the background research on cooling towers, to keep it simple, you have hot water into some type of system, and in this case, our system was which is a cooling tower, and then you're going to have air and water that's cooling that water down, and then as it exits, it's basically a different temperature that when it went in. And this process is basically some type of heat exchanger. So speaking of heat exchangers, we have several of them in our lab equipment. And all of them serve the same purpose. They're trying to cool down some system, but using a different method. And so in order to start our project, we researched each of the functions, capabilities, and limitations of each heat exchanger and incorporated that into our design. So the first one we're going to look at, which is a double heat exchanger, and to also keep it simple, is basically another liquid cooling down another one, but there's not going to mix at all. And again, this is a lab equipment that we use. Same setup, same heat exchanger, using the same process, but this time we're using air to cool down. And then kind of like the first one, there's a shell and tube heat exchanger, and the two liquids are not mixing, but again, you're still trying to cool down another liquid.
So we asked ourselves, what do we want to do for this project? And we said, we want to leave a legacy behind. We want to leave those engineers coming after us something to work on. So we came up with this idea of having a cooling tower where it's visible and see-through, and you could actually touch it and work with it.
So as I discussed the different types of heat exchangers, one of the heat exchangers that you did not hear that's not in the lab is basically the cooling tower. So we wanted to basically implement or put in the rotation in the lab our design. And basically that includes water and air, which other heat exchangers did not. And then we also wanted to add a certain capability of our heat exchanger, was basically we want future engineers to be able to design a part, implement that part in our design, and then be able to actually get some type of calculations from it. So in order for our cooling tower to be successful, we knew that we wanted to be visual. Therefore, the user can see the process of all the process that occurs in the heat exchange, and also to make it very hands-on, hands-on learning. But our main objective, again, like I said before, was we wanted that engineer to be able to design a part, implement that part into our system, and then be able to take calculations on something that they designed.
Cooling towers are categorized by their design features. So for example, natural draft cooling towers use air buoyancy to facilitate air travel. Mechanical draft cooling towers use a fan or a blower to introduce air into their system. Cooling towers with fluids flowing perpendicular to each other are considered counterflow, and cooling towers with their fluids flowing in opposite direction are considered counterflow. Additionally, cooling towers may also be open circuit or closed circuit. In an open circuit cooling tower, the process fluid and the cooling fluid have direct contact with each other. In a closed circuit cooling tower, the process fluid and the cooling fluid do not have direct contact with each other. To achieve our goal, our group decided to design a closed-circuit mechanical draft cooling tower that would include a fill, a clear plexiglass housing, and quarter-inch copper tubing. Design considerations and specifications that we took into account were a temperature range of 5 to 60 degrees Celsius and a flow range of 1 to 65 liters per minute.
Here we have one of 20 drawings for prototype 1, which is the base of the first prototype we have here, and it has grooves on all 4 sides to set the plexiglass in place. Here we have one of 28 specifications for prototype 1 as well, which is the pump, 12-volt solar hot water heater circulation pump. And here's a picture of our first prototype to the left.
This is the emptying analysis. As you can see, 60 degrees of water will be going into a tube. The material is copper, and we have 2 passes right here.
Here's a short video of our first prototype working mechanically. As you can see, hot water runs through the copper tubing while also being cooled down with room temperature water circulating in the system. And we have an LCD screen which shows the temperature readings and the flow rate. Even though our system worked conceptually, we wanted to improve on the sensors, the manufacturing aspect, and an easy way to interchange the tubing material. Here we have one of 7 drawings for our final design, which is the lid, the circles on top are for the fans. Here we have the specifications, 1 of 35. We have a quick disconnect where you could easily connect and disconnect all the tubings. Here is a picture of our final design.
As you can see here, we're using Arduino schematics. This is the Arduino right here. Those 3 here are temperature sensors, and those are we're using to capture the temperature here in the system.
Here we have a stress analysis of the plexiglass enclosure and the base. The materials were plastic for the shell and aluminum for the base. We applied 20 pounds of force, making our safety factor 9.66.
As you can see here, I'm using the same materials and the same settings. The only difference here is it's much larger and it also has more pass. There's 4 passes right here. And the reason why we did that, because we wanted to have more heat transfer in our system. This is our final design of our video. As you can see here, the red water is our hot water. It'll be going into the system and be cooling down and go back to another DMX. The system is being cooled down by 2 of our fans, as you can see right here. And the blue water, as right here, is going back into the bottom and going up as recirculation.
Here we have evolution of our prototype. This is our first prototype, which we designed and manufactured. And here we have our final design, which we have an evolution from our smaller one to our final.
All right, so now come to, in my personal opinion, which is the coolest part of our project, which is actually having the future engineer or the lab student or the user actually exchange or take out the part that they're actually going to design. So Freda's going to demonstrate how to take that interchangeable part out safely.
Here we have a lid with fans. Here we push this quick CPC connect and we have our nozzle. Here we reach in for our mesh and we can easily set it to the side. This disconnect, we press a button here and press another one here. And we easily have access to our tubing.
So we want the student to interact with our system. One demo software was using LabVIEW. This is a screenshot of the computer. The left side is our temperatures. So Arduino will be sending that to LabVIEW, and our right side is the flow rate.
To progress to our final design, we modeled the heat transfer in our cooling tower as heat transfer across 2 banks, and introducing process fluid to our cooling tower at 60 degrees Celsius at a flow rate of 3 liters per minute, gave a theoretical out temperature of 51.5 degrees Celsius. After conducting experiments and testing our final design, we came to an outlet temperature of about 30, 35, 37 degrees Celsius, while trying to keep a process fluid consistent of 50. However, we were unable to maintain that, and we kind of got it consistent at around 40 degrees Celsius. And what you see in the gray is just the temperature of our cooling water. It started off at 20 degrees Celsius, and through time, it reached a steady state temperature of 25 degrees Celsius.
Before anyone begins to use our product, we encourage them to read our assembly manual, our operations manual, and our parts list. So it all comes down to cost. How much did our project cost us? And it came out to be, our final design came out to be $808. And if we were to mass produce it, one out of 1,000 would come out to $485. So we asked ourselves, where can we use this product? And we told ourselves, this thing could be incorporated into middle schools, high schools, universities, and training programs for plants.
In conclusion, our goal was to design, fabricate, and test a cooling tower that could be used as an educational tool for a better understanding of thermal fluids, heat transfer materials. We believe we achieved our goal by designing a closed-circuit mechanical draft cooling tower that incorporates a clear housing for a better visual understanding, interchangeable parts so that future students can incorporate their own designs, and a LabVIEW user interface system that can that allows for real-time controls and real-time data acquisition.
All right, so that pretty much concludes our presentation. We want to send a special thanks to the companies that you see above on the slide, especially to Instar, which is where the effort we work at. We were able to do the same presentation in front of the CEO and some board members, so they gave us a lot of criticism and feedback, so that was kind of cool. And also to Dr. Garcia for actually bringing us along. So at this time, I guess we will take any comments and questions. Yes, sir.
I preface this by saying I don't know much about heat exchangers in my life, but is 8.5 degrees Celsius of cooling or what?
The one, I'm sorry?
Is 8.5 degrees Celsius of cooling a lot of cooling?
It depends on the system for are you referring to our theoretical?
Yes, right. So I think it started off at 60 and went down to 51.5.
For our system, it is, and the reason why that happened is because we modeled our cooling tower as heat transfer across two banks, but in that case, you're introducing temperature in each tube at 60 degrees, and that's really not the case in ours because really we have 4 inlets and not, I guess, 16 inlets, if that makes sense.
Not too much.
With
This other concept.
Oh, okay.
Any other questions?
Yes, sir.
So your FEA analysis or your heat analysis, it was heat, not stress, right?
Yes, heat.
Okay.
Well, we have heat
It
and
looked pretty
stress.
gorgeous there, and then you did this physical analysis. Did you compare the two to see what your error is in your theoretical model? Does that make sense? So you have this model, and then you ran physical experiments, yes?
Yes.
So, did you compare the two to see if your theoretical model is correct?
What we noticed is that our theoretical model was a bit more exaggerated than our physical model. we would like to do like more tests of what we got from here, because, we weren't really sure like how we wanted, our settings to be. And we weren't, basically sure, because we know that as soon as, right here, it wouldn't be 60 all the way here. It would be like 60 here, and then dropping. And of course, each side will be dropping also. But we don't believe that it will be going this much. As you can see here, it's dropping too much. But in real life, we kind of dropped around 5 to 10 Celsius around that time.
Yes.
Mhm.
Yes, sir.
So what did you do for calibration? Is the temperature that you see accurate?
Calibrations as in for the temperature probes?
Yeah.
Yes, we have to manipulate, as in we used one of the K-type sensors, and we dipped it into the same water system to make sure they were matching the same amount, and yes, they were calibrated the same.
Any other question? I think that when you guys did the FEA analysis, there has to be one assumption, and most likely is because it might look like that entity is completely soaked at exactly the same temperature rather than being water sprayed on it.
Yes.
So when you're doing that kind of assumption, is throwing the whole calculation out because it's meaning that you have an excessive amount of heat transfer, even in that just short period of time, because the rest is still, you still have like 2 loops
Yes.
at the same temperature. So I think it's one assumption that needs to be corrected into that.
Did you do any hand calculations to predict what you might need in terms of sizing and how it would perform?
We performed the energy balance, and then we modeled the heat loss as heat transfer across 2 banks, which was in the previous slide as theoretical.
That's it? That's it?
Yes, sir.
Can you go to that?
That's what you have. No.
Theoretical.
Go on. You went too far.
Go ahead.
That's the theoretical results, but the hand calculations are not shown there.
This is a result of some hand calculations
Yes, sir.
Yes.
that you attempted.
And Excel.
Assuming it's 60 degrees going in, and using, natural water off a faucet.
What was your methodology? Just, I don't need the details, just roughly, how did you tackle that problem?
We took what we knew that we were going to have copper tubing and feeding us 60 degrees, hot water at 60 degrees, and for there we calculated what the surface temperature would be on the outside, and then from there we modeled it after heat transfer of fluid across 2 banks, and then we started getting heat transfer from there, Reynolds number, Nussbaum number, and our convection coefficients and whatnot.
Any other questions?